Thank you all so much for coming tonight. It's a miserable night, and welcome. Those that walked, please put up their hands. Those that rode a bike. There we go. There's one, two. Excellent. Well, welcome to everyone, and thank you to the University of Victoria Retirees Association for organizing this. I happen to be the chairman of the organizing committee, so I'm really thanking myself. And this is the first of a 9-part series on living without oil. And I thought I'd make the case for living without oil so that it would help you step through the other 8 lectures which are ahead of us. I also like to thank ICEVic, that's the Integrated Energy Systems group in the university here in the Department of Engineering, who are very supportive in this, and we've worked collaboratively. They're providing a lot of the speakers, as you'll see, from the program, but we've also got a number of speakers that are coming in from out of town, which is always a challenge in the wintertime. But with your permission, each of the presentations will be videotaped, and John here has kindly organized a setup with the fixed cameras. They will be always facing this direction, so if you have any objection or worries about your face being in them, I don't see that as being an issue. But again, if it's with your permission. And this is for teaching purposes, and of course the videos would be made available along with the presentation in some format, and we have yet to decide how to do that. So who am I to make the case for living without oil? I was born in Yorkshire quite a while ago in northern England, in the same year, as a matter of fact, that the single largest oil field in the world was discovered. Does anybody know what that is? It's in Saudi Arabia, and the field is called Ghawar, and it was discovered in 1948, so that tells you how old I am. And amazingly, it's still producing today, and along with 4 other supergiants, also in Saudi Arabia, it provides 10% of the world's daily needs in oil. That is 10 million barrels a day. That's 10%. So you know now that the daily consumption of oil is 100 million barrels. The Saudis are most secretive, of course, but we do know it's in decline, and so it should be. I think anybody who's lived 70-odd years is in decline. And so too is the oil field, and the decline is through natural depletion. Well, I became a geologist in the UK as a passport to leave the grime-covered buildings and the thick fogs of northern England in the 50s and 60s. And just as an aside, I chose to be a geologist to get that passport out of England. And in my graduating year from Durham University, I was privileged to look down a microscope at the first lunar rocks that were returned to Earth. Not returned, but came to Earth in 1969. And it was a life-changing experience for me, and I was delighted that I'd chosen geology. The rock samples were absolutely phenomenal to look at under a microscope. And someday I'll tell you about it on another course. And I went on to complete a PhD at Queen's University in Kingston, Ontario. I then joined Shell, so there's my disclaimer. And I spent the next 30 plus years looking for oil and gas deposits around the world, exploring the world for oil and gas as a geologist and as a geochemist. It became clear the industry was changing quickly, especially in the latter half of the 20th century, just when we came to the end of the 20th century. And conventional oil and gas deposits were becoming increasingly harder to find. The industry was starting to focus on drilling and fracking unconventional reservoirs, by which we mean reservoirs that don't yield up their oil or gas very easily because they're tight, they're very fine-grained. And for that reason, we have to frack them. And of course, we all know that's not a very acceptable thing to do, or a large body of people object to that. It's a subject of much controversy. And I saw no enjoyment in continuing. So I came to the island and retired. And I retired to Nanaimo, and that's where I started to teach some geology courses at what was then Malaspina University College. And one of my students, in inverted commas, approached me after one lecture that I had given, and his name was Joe Sieber, and he asked me to help him. He had conceived a technology to extract energy from waves. And he had 2 patents protecting this technology. He was stuck and he didn't know what to do. And so I formed a private company with him, and we raised a few $1 million, formed a partnership, and then approached UVic here, the institution that I mentioned earlier on, and came into contact with a bright young engineer, and we went on to try and commercialize it. And as a matter of fact, Brad Buckham, who's the name of the engineer still at UVic here, will be speaking on this on February the 29th. It's a weird day because it's a leap year, but that's when he's agreed to speak on it, and he will update us on the state of that technology. But this topic of living without oil is huge. It is complex, and it ties in with a need to understand climate change. It brings together scientists of all types, biologists, geologists, geochemists, physicists, even astrophysicists, to help us understand the role of the sun, which you know is key to the carbon cycle, and the formation of fossil fuels. Without it, none of this would have happened. The cause of all our problems, I might add. There's a lot of chemistry and biology, and processes are not easy to understand, and certainly not easy to model with any degree of confidence. It's a subject which brings together engineers of all types, not just scientists of all varieties, but whatever a climate scientist is. I'm not sure what a climate scientist is. Is he a physicist or a chemist? I'm not sure. But it brings together engineers of all types. It brings together sociologists, businessmen, and investors. And it brings together philosophers and, unfortunately, politicians. And maybe it divides rich from poor. Something to consider. But it basically involves everyone. We're all affected. It's the most complex of subjects, and it exposes how little we know of our planet. And how did we get here? Where are we going? It's taken us 4.6 billion years to get to this point. And we have another 4.5 billion years to go before we get swallowed up by the sun. It's a frightening subject, and the solutions and the alternatives are by no means clear. So that's a sort of a preamble to what I have to say today. And I've got an extensive group of slides. And the first slide asks the question, why do we need to consider living without oil? And I'd suggest there are 2 reasons. Firstly, we're exhausting supplies. And secondly, from an environmental position, it's the right thing to do. How do we do this? Well, we need to reduce our consumption of hydrocarbons. And let's face it, we'll never eliminate using hydrocarbons. I hope to demonstrate that. And if anybody's come here tonight thinking that we are actually going to get to a point where we can live without oil, I'd like to talk to them. So, and really what I'm talking about is not just oil. I'm talking about hydrocarbons. So that obviously includes natural gas and to a certain extent coal, well, definitely coal. But those are the 3 commodities: oil, natural gas, and hydrocarbons. So to reduce our consumption, we need to improve our ability to replace energy from non-hydrocarbon sources, alternative sources. And we'll be talking about that throughout this particular series. So reduce and replace. Those are the 2 ways on how we can do it. And if we do both of those things combined with sequestering emissions, we have a good chance of realizing the Paris Agreement, the ambition to limit global warming to 1.5 degrees C in the next 50 years or so. So, to achieve that, we need to achieve net zero emissions by 2060 or 2070, somewhere in that time frame. This gentleman, Colin Campbell, in 1998, he was an Amoco geologist, and he forecast that there would be a peak oil occurrence and that it was linked to a peak in the population of the world. He formed the Association for the Study of Peak Oil in 2000, and he actually kept predicting when oil would peak, because as he got older, the peak hadn't quite arrived. But here, in 1998, he predicted it would peak in 2001. And I think we know that it didn't peak then. It may be peaking now, but it's a very hard thing to say, yes, it's peaked. But this is a very interesting quote given by a compatriot of his called Youngquist. The end of the petroleum interval will be gradual, wherein no crisis point is reached, just slow change. But especially with rising populations and no sufficient substitutes for oil at hand, there is the possibility of a chaotic breakdown of society. So there are two imperatives which I've mentioned. The planet is running out of oil, hydrocarbons, and burning hydrocarbons at the current rate is causing runaway global warming by rising greenhouse gas emissions. And if those aren't sufficient, then I don't know what it would take for us to consider living without oil. And so as business as usual, we anticipate greenhouse gas emissions to continue in the path forward for the next several years of this century, in fact, to the end of the century. And this is something that came out of the Paris Agreement in 2015 and the IPCC Special Report on Global Warming. And it really suggests that, what did you do with the clicker?
It's on the top, on the computer.
On the left. Behind your
This-
computer on the left.
Oh, thank you. So this is the future as business as usual, but what's being suggested is that we need to reduce our emissions and follow a pathway something like this, where we need to substitute and reduce consumption, which is shown in blue, and at the same time we need to start to sequester some of those emissions that we emit, and until we put a balance here. And this is the net zero line, and that occurs at 2065 or 2070, according to IPCC. Looking at it in a bar chart, I think this is a little clearer, and in fact they offer an alternative goal where the one that we're talking about limits warming to 1.5 degrees C, net zero emissions somewhere around 2065. There's an alternative proposition of limiting it to slightly warmer, 2 degrees C. So let's look at where the sources of energy are in the world, and I've divided them into two groups. The black ones, of course, are hydrocarbons, the dirty ones, and they produce somewhere between 84 and 19, perhaps even a little more, % of the world's energy. Included in that is biofuels, which is interesting, and we'll come to that later on. But in green are listed what we might consider to be non-hydrocarbon sources, and they currently only account for about 16% of our energy. And I've listed them there: geothermal, nuclear, hydro, solar wind, tide, wave, and hydrogen. And these are the sources that we're going to talk about as we go forward. We're going to end this presentation in a little while, after we've had a break and so forth, with the work that's being done by Shell. And that was my disclaimer initially. I have no role in this at all, but it just so happens that Shell have done a wonderful job in in looking at a pathway where we can change our way of consuming energy and reducing emissions and achieving the Paris ambition, as I will say repeatedly in this particular presentation. And you can see there's a circle there which says today in the middle of it, and that's the makeup of the energy consumption in the globe today. You can see that green is natural gas, this is oil, this is coal, and these are the biofuels. And the non-hydrocarbon sources just make up this amount here. According to Shell, this accounts for 92% of our combustible fuels today. Those four commodities, oil, natural gas, coal, and biofuels. What they're suggesting is that in the year 2070, there's going to be a growth in overall consumption. Population's growing. There's several reasons why that would be expected. But what they're suggesting is there is a pathway, which I will come to at the end of the talk, which suggests that we will have reduced our emissions to our makeup of fuel to 36% combustibles from 92 or around 90. And you'll see that the makeup is quite different. I'm giving you the end before I've begun. But you can see that solar and wind in pink make up the bulk of the source of energy. Nuclear, interestingly, goes from 5% to 11%. I'm rather disappointed at that because I think that's not, never mind, we'll come to it. But let's talk about how we have and continue to use energy. So we're burning hydrocarbons, and the sources are from either fossil fuels or biofuels. And when we do that, of course, it's all hydrocarbons, and we emit CO2, and that's the elephant in the room. There are two sides to this chart. There's the energy consuming side. So we're burning hydrocarbons to provide and meet our transportation needs, our heating needs, in smelting industry, our cement and manufacturing and fertilizer. Even petrochemicals fractionation is just the heating that's required there. And of course, in the generation of electricity, both from coal-fired sources, oil-fired sources, and gas-fired sources. On the right is something which we often forget about, is linked to hydrocarbon combustion. And the reason why I think we can never live without oil, because we depend on the petrochemical products that are listed there. Everybody's wearing some fabric which is made from petroleum. We have carbon fibers and resins, the tires that we use, paints, plastics, ammonia, fertilizer, explosives. It's just huge, the breadth of products which derive from oil. And to say that we're going to live without oil and still use these things is absolutely fallacious. I don't know how we would make these things, or if we need them. Do we need them? I would think we would. I think people need their pharmaceuticals. Here's an interesting picture, and I came across this 15 years ago, and I can't remember where it was. I think it was in the National Geographic. Some of you may remember it. I've put the date 2003, but it's possibly wrong. But it struck me. It's a picture which shows everything in it made from hydrocarbons. You've got bitumen shingles on the roof, the siding on the side of the building, and goodness knows what is all made from plastic and various things of that sort. Even the carpet, and it's an astonishing photograph. So let's go back to that slide that I just showed you and said, well, what can we replace to reduce our consumption? And I've put in green what I think we can move towards eliminating the use of oil, gas, or coal. And through electrification, I think we can move in the direction of providing all our transportation needs, except for marine and aircraft. I think we've got real problems with those two. And I've suggested aircraft, maybe hydrogen down the road, and in fact Shell makes that suggestion as well. I don't quite know how that's going to work, and in fact we have one talk on hydrogen that might well explain a little bit about that. But on the marine side, we've got these big ships moving around, all the cruise ships spewing out emissions, but consuming diesel, bunker fuel, and yet we know we can, from looking around the world at navies and nuclear submarines, that there are small modular reactors that could power these vessels. And maybe that's the direction we have to ultimately go in. Otherwise, we're stuck with using bunker fuel. On the heating side, I think we've always got a problem in smelting iron ore. We need to use coal for that. It's just part of the metallurgical process. Similarly, cement, it's a great consumer of hydrocarbons. Not just in burning it and retorting it. And of course, fertilizer itself is a huge consumer of hydrogen, which is largely made from methane, steam reforming methane. And so those are three things: the blast furnaces, steel, cement, fertilizer, where I think we've got a bit of a problem. We can't get away from hydrocarbons, and mainly the coal side. But other heating needs and commercial buildings and so forth, and electricity itself, of course, we're going to come to how we might be able to provide that. But on the right, the elephant in the room is the fact that we can't do much about the petrochemical products. How do we replace oil to produce those? Now, this is a slide which I got from Ballard, and Ballard are coming here not this coming Saturday, the next Saturday, February the 8th, and talking about the fuel cell and hydrogen, as I've mentioned. But this particular slide struck me some years ago, and it really shows the years along the bottom, 1850 through to 2050. And it sort of pictorializes the decreasing carbon, or the decarbonization, if you like, of society, and how in the early days, of course, there was a high consumption of wood, which was in decline, and that was taken over by coal, which reached its peak. We'll talk about that, and it's been declining. Oil is somewhere where we are now, at the peak of, and then we've got natural gas and nucleus down here, and then some alternatives here. So I thought this was a very sort of insightful sort of presentation, but the move is towards a carbon-free environment. Let's just review uses of oil, just so we're all thinking that it's really quite a commodity that we have to depend on. 100 million barrels a day, decreasingly used to generate electrical power. 95% of the world's transportation needs are met by using oil. It's a very convenient fuel. And that means 45 million barrels of oil every day is used in transportation. Manufacturing, and this is just in the US now, we use 1.25 million barrels of oil a day in the US for producing plastics and artificial fibers that we mentioned previously. And asphalt. What would we do if we didn't have asphalt to drive on? Would it be gravel? Perhaps it would be cement, but cement presents a problem, concrete. But there is a large consumption of use of asphalt to create the highways and the streets that we drive on. And in the US and Europe, it's about 1 million barrels a day. Not a whole bunch, but enough to worry about. So these are the sources of energy that we're going to be talking about. Now, this series does not discuss biofuels and geothermal. I couldn't find a Saturday where we could squeeze that in. And so I might mention a little bit about that in this presentation. So here's the series coming up. I won't go through it in detail. I think there's a handout which lists the talks, and hydrogen I've mentioned, which is the first one, and then solar, wind, and then wave energy. And that's the first part. That takes us through to the end of February. The second part is for March. And we're going to start out in March with a presentation from BC Hydro, because, as I've inferred, there is a huge requirement to increase electrification. The question is, where's it going to come from? What are BC Hydro's plans? What are the needs? What are the actual needs? Do we know? Do they know? That's probably a question to ask of the Heather when she comes here on March the 7th. I'll prime her that you're going to ask her. Then on March the 14th, I have to confess that there's been a bit of a change here, in that John Stewart, who was going to come from Ottawa, has now changed his plans, so we're going to switch things around a little bit. But I'm looking forward to his talk, because he's going to talk about these SMRs, so small modular reactors. There's no need to build these big multi-billion-dollar behemoths that are at risk and really create a whole bunch of problems. We could deal with very small modular nuclear reactors in a very safe manner, and he would like to talk about that. And then Andrew, I don't know if you're here tonight, Andrew Rowe, he's the chairman of ISFIC. He's going to present to us how we can store electricity. This is one of the biggest problems that we face, is that when we produce electricity, it's produced now and has to be used now. There's very real problems of storing it. And of course, batteries are increasingly being developed with a high degree of sophistication, and he's going to update us on that. And then at the end of it all, on the last day of the series, we've got this panel discussion. And I've got a number of people who are knowledgeable about this whole subject, and we're going to sort of sit up here and see if people would like to ask questions, and we can also get the panelists' point of view on a lot of what we're talking about. So living without oil has been covered in all sorts of news articles. The end of cheap oil. Anything into oil, meaning, we can make oil out of anything. You can make oil out of coal. The Germans did it in 1926. You can make oil out of gas. You can liquefy. Gas to liquids is really what it's called, GTL, gas to liquids. World's oil supply outlook, not so bleak, not so rosy. Now these are a little bit old, but there are numerous publications. Saudi oil, ample or apocalyptically low. And that's the big issue with the biggest producer in the world, is that we really don't know what they have left in the ground. And of course, there's all manner of textbooks, and I took a photograph of the books that I brought along here, and during the break, perhaps we can, you can come up and have a look at them. Some marvelous titles: The Party's Over, The End of Fossil Fuel, Twilight in the Desert, that's a tremendous one by Matthew Simmons. Resource Wars, Michael Clare, that's an excellent read, with diminishing supplies of oil and tighter supplies and choke points such as the Hormuz Strait and so on. He covers all that in that book, but it's not just oil. It talks about water as well, how there's some potential for wars, conflict, if you like, over the distribution of water, which isn't very equitable throughout the planet, as we know. So there's some very interesting books. Oh, and the other one, The Planet Remade, which is a new text. This one here by Oliver Morton. That is one of my favorite books. And it talks predominantly about geoengineering. If we want to change the climate and have control over it, you've got to read that book. So back in the 70s, there was the Club of Rome. Raise your hand if you knew about the Club of Rome. So some people have heard of the Club of Rome. It was an organization that came up with this publication in 1972 called Limits to Growth. And what they predicted was a declining availability of resources. So let me just show you on these charts here. We've got years on the bottom, and we've got the year in which it was done, 1972, in red in each case. And then we've got an update which was done by MIT. And so what they did, what MIT did with data for 2010, published in 2014, I guess they took 4 years to do it, weren't in a hurry. But they took the curves which were put, the information that the limits to growth people, the Club of Rome came up with, and extended it. And it roughly follows the projected forecasts that were made back in 1972. So, interesting title, Limits to Growth Was Right. New research shows we're nearing collapse. And it's this whole issue of collapse which is of real concern. This concept of general adaptation syndrome was first suggested by this Canadian endocrinologist, Hans Selye, quite a few years ago, 1936. And he detected it in rodents, and that is that the population grows exponentially, achieves a point, and then for whatever reason declines very rapidly. And this gentleman, Australian Reg Morrison, who's a bit of a thinker on a lot of these subjects, captured this by calling it the plague species and attached it to the population growth, which you can see in the curve here. So going back to 1300 and now taking it through to 2100, the end of this century. He postulates that population will peak at somewhere around 7.2 to 7.4 billion people in this time period here. But you can see how rapid this growth has been. And he's suggesting that there's tremendous decline after that. And that this is true of many populations and species. Here's a study that was done on reindeer, and it shows that there was a similar sort of peaking and then the decline, a resource collapse. And the humans on Easter Island obviously used up all the resources, and as a result they reduced their own population through starvation in one form or another, and eventually it collapsed. And in fact, there's a very good book, did I bring it? Yes, Jared Diamond. It was published quite a while ago, but revised in 2011. And he's a powerful author, and just a quote from him: the root problem leading to collapse is overpopulation and the carrying capacity of the environment. One of the main lessons to be learned from the collapses of societies is that a society's steep decline may begin only a decade or two after the society reaches its peak numbers, wealth and power, etc. The reason is simple: maximum population, wealth, resource consumption and waste production mean maximum environmental impact approaching the limit where impact outstrips resources. So it's a very sobering read, and he visits all sorts of societies around the world that have demonstrated this idea of rapid growth collapse. But he offers a positive suggestion. He makes some suggestions to people as to what they can do as an individual. So it doesn't leave you hanging. It offers some suggestions, which is kind of nice of them. Now, Reg Morrison, this Australian that I spoke of, made the observation that the UN were collecting data and publishing it on world population growth. So just let's look at this chart for a moment. In purple here we have zero growth. And then we have increased growth in percent per year. And of course on the bottom here we have the number of years. So we're going back to 1940. The collected data showing that the growth in population was increasing through this period of time here. And then the UN stopped reporting because it was too negative. I think they were concerned that they were upsetting people. And so they thought, we better not mention this anymore. But nonetheless, you can see that there was a peaking here. And we're back trending towards zero growth, which is what I think we need to see. We need to get that population growth under control. And why it occurs, well, that's for others to debate. Pandemics, which is an interesting thing to talk about now. So the ecological footprint that we have, again, Reg Morrison came up with these numbers, which I think are very insightful. Earth's surface is 51 billion hectares. It's a lot of hectares. 71% covered by oceans, which means that 14.5 billion hectares are land. But of the 14.5 billion hectares, only 8.9 billion hectares are productive. The world population is $6.9 billion people at about this point in time, which, doing the calculation, means that you need 2.1 hectares to support each person, and that's our footprint. Well, it turns out that we've only got 8.9 billion hectares of productive land. So we need 1.6 Earths to meet the needs of our current Earth population. Well, unfortunately, we don't have 1.6 Earths. We're 55% over current carrying capacity, and we reached this point in 1980. This limit was reached in 1980, so we've outgrown our Earth. And I just want to read this because it's this Faustian penalty, which again is Reg Morrison's words. Since the energy and resources consumed by our species already amount to more than 1.6 times the biocapacity of the entire planet, it means that we are consuming its resources 1.6 times faster than the Earth can replenish them. And so in economic terms, we are asset stripping our cosmic home and shrinking its carrying capacity on a daily basis. If this growth in population energy consumption continues, by 2050 we will need the resources of 2 Earths just to sustain our population at its present level of consumption. Our species will then be ecologically bankrupt and primed for a swift extinction. Very, very difficult words to read. This is an interesting curve, and it shows that before oil was discovered in the United States, there was this normal distribution of whale oil, sperm oil, and whale oil imports into the United States in gallons. And then the first oil well was drilled in 1859, and that kind of saved the whales. There was no need to slaughter the whales, at least for their oil. Now, going back to Campbell and Lahare, this is an interesting curve which he put out in 1998 in the Scientific American, and it shows a number of curves, again illustrating this concept of peak oil. And we've got a production peak that was estimated, this was done in 1998, that the peak oil for the world, shown in red at the top, would be in 2004. And maybe we are about there now. Maybe we're a little bit behind. Interestingly, let's look at the US in brown here. Because in 1956, which isn't highlighted other than the point that I just made, is that in 1956, King Hubbard was a shell geologist, and he, at that time, in 1956, made the prediction that in 1970, the US would achieve maximum production. And indeed, that did occur, and we'll come back to that later on. It's quite amazing, really, that he was able to predict that. But Campbell made a series of other follow-up forecasts, and again, this curve was generated in 2001 and shows not just for oil, but for gas as well. It doesn't include coal, however. And the curve looks no different than what he did another 7 years later. And so he's still clinging to the idea that we've got this peak oil occurring at some point in the near future. Going back to the US peak oil, here we have the US production. And he was bang on, King Hubbard was. In 1970, the US produced 9.64 million barrels a day. But hang on, what's happening over here on the right? Well, this is shale oil, and this is what's happening now. This is why I left the industry. I don't enjoy shale oil. It's not exciting. Looking at U.S. crude production, just the tail end of that, again, analyzing this shale oil peak a little bit more, you can see that there's been a rapid growth, they call it the Trump curve, heading up to the right here, and we're up around 12 million barrels a day. Well, we just mentioned that peak oil in the US was 9 million barrels a day. But this is what's happened. There are these 5 states, Texas, New Mexico, North Dakota, Colorado, and Oklahoma, where these oil shales occur and which are being drilled at a furious rate. It is an absolute treadmill. And what you see here is the same part of this curve. And in each year, you can see the wells that have been drilled in that particular year. This year, 2012 to 2013, and you can see the pink here is quite significant, 2 million barrels, and then it declines rapidly. And it's a treadmill. Every year you have to drill a huge number of wells, frack them, and of course this is more expensive, it's more energy consumptive, and it's a very difficult way of keeping your oil production up. Looking at this a little differently, here's another plot of US oil production. In red is the conventional stuff, and then the deep water was discovered somewhere around 1960, the deep water Gulf of Mexico, and that's this blue color here. Well, the Alaska North Slope was discovered in 1964 and came on stream in 1970, and it continued to produce through here. And then now here we have the shale oil. Let's talk about Alaska. Discovered in 1964, thereabouts, came on in 1970 and achieved 2 million barrels a day from different fields, mainly the big field, the big giant field here in blue, but smaller fields which are often found after you've gone in and found the big one. And of course the Trans-Alaska Pipeline was built with a capacity of 2 million barrels, because that's in fact what the peak capacity was. However, there's an economic limit here of 250,000 barrels a day, and so this will be shut down at some point. And there are no reserves coming on stream behind this. The same is true of the North Sea. The North Sea, made up mainly of Norway and of the United Kingdom. You can see that discoveries were made just when I graduated in late 60s, and fields came on stream, reached peak production, and now have declined. And that's true of both Norway and the United Kingdom. Strip out the United Kingdom, and again we find the individual fields, the big ones being found first. These are these big colors here, but all these smaller ones were found afterwards to give you this right-handed tail. So to summarize what we've talked about here is that I feel strongly that all these things are coming to an end, and that if we look at the history of giant fields that have been discovered, they're shown in gray here going back to 1930. And I mentioned Gawa here right at the outset, and here it is. It's a little bit smaller than it actually is. It's probably more like 80 billion barrels. It's shown here at 56 billion barrels. But these are the years in which the big giant fields or supergiant fields were discovered. And you can see the field size is declining. We found all the big ones in the world. We're very good at it. I don't mean to brag, but this is conventional oil, and we know where to look for it, how to look for it. And it's been fun, but it's over. And really the future is predicted to not produce very big fields in the future. So we are coming to an end. And our current production here is 35 billion barrels a year. If you take roughly 100 million barrels a day and multiply it by the days in the year, you end up with about 35 billion barrels. And so we're doing okay. We're still managing to squeeze this stuff out of the ground, but it's a growing gap. So the second reason that I think we need to consider is that climate change, which is linked to GHG emissions. And this really brings about some anxiety amongst people, I find. And so we've put together this May Climate series. We all know that global warming is taking place. I just want to go over a few things, and then we'll take a break. But key amongst them are discussing how do we know that global warming is happening, and what possibly are the causes for it. Greenhouse gases, what are they? I won't talk about the carbon cycle. I've taken that out. It's just too complex, too detailed. It takes too much time. So then I'd like to talk about sequestration, and we'll take a break. Here's positive proof of global warming. I won't keep that up too long. But now that's that one dealt with. We need not to consider it anymore. Here's a very instructive chart. It shows 400,000 years of history, corresponding with ice cores over this period of time. And here we are at the present time. And it shows three things. It shows in red the temperature change from the ice cores, from isotopic information and so forth. And it also shows methane. Methane is a greenhouse gas, and it's shown in black. And it's upwards and downwards and so on. And then carbon dioxide, which we're going to come to at length shortly, shown in this gray. And today we're at 415 ppm. You know, the CBC tell you what the carbon dioxide content is every day at 7:45. You need to tune in and find out. They'll say it's 413.68 today. And you're supposed to conclude from that something, but I'm not sure what. But as you can see, it's fluctuated over time. And yes, it's up here. But the interesting thing about this curve is that our current temperature is no different than the interstadials, the warm periods in between the glaciations. And these glaciations, they occur with a certain rhythmic occurrence. We've got a cooling trend here that starts us off. And it comes out of a temperature high that's probably very similar, if not higher than what we are today. And that's 400,000 years ago. And we keep doing this, and we keep doing it, and we keep doing it, and we keep doing it. So where are we going? We're told we got to watch out because we're just runaway global warming. But I just put this before you just to make the point that, you know, there are some other views, and whether you call people skeptical or whatever, I don't think, you know, I showed you that previous graph, and there's clearly global warming going on. But this is an interesting series of curves. And the methane, well, now the methane is way up there. Now, why is that? There's another story here where I don't have time to go into it as to why the methane might be that high. And similarly with carbon dioxide. So let's look at the temperature of planet Earth. We've acknowledged that Earth is currently experiencing a period of global warming. And I'd like to put this into context now. This is something which will be explored in more detail by Tom Gallagher, who's sitting there, and he's going to give the second talk in the climate anxiety series. Not to put you on the spot, Tom. That'll be in May, second week of May. Here we are at the end of what we call the Phanerozoic, and this is a period which lasted 542 million years. And we've experienced a whole bunch of warming, cooling throughout this 542 million period. We're currently here at the present, and we've come down here. What we have is the Cenozoic, which started 55 million years ago. The Cenozoic means new life. Mesozoic means middle life. Paleozoic means first life. So this is really recording the history of life on Earth. Forget about the previous 4 billion years. Let's just deal with the last 500 million. And of that, let's just deal with the last 55 million in the Cenozoic. And this is when, of course, 55 million years ago, what happened? Asteroid impact. And that's a huge extinction. But we were then led to a new lease on life, the Cenozoic. And I'll come into the biospheric aspect of this later on. But let's expand this period here into a series of panels. Let's forget about the early part here and go to the start of the Cenozoic, this green here, which corresponds with this green. I've expanded it. So this is 55 million years, and we get it down to 10 years. Then we expand it again and go to 1 million years. And then we expand it again and go to 20,000 years, and here we are today. And here is the temperature. It's come down from the asteroid impact. It's falling, and this line here indicates pretty much where we are today. And there's that diagram again. And that diagram is outlined in red. And there have been 10 glaciations. These are 10 of them. Count them up. 1, 2, 3, 4. 10 of them. This period here corresponds with the red shape, and there are 4 of them shown here. We talked about those. And the last glacial maximum is what we're coming out of right now. But of course, the time scale's really enlarged. So there was the 10 glaciations with that blue dotted line. And humans, Homo sapiens, came on the scene somewhere around 300,000–400,000 years ago. And they must have endured quite a hardship, wondering what the heck was going on. And they didn't prosper very well. We didn't see that population growth that we now see. We had to wait until the Holocene. And the Holocene is this blue area right at the end here, and covers about 12 to 15,000 years, and it's expanded here. Just before I leave this, though, there are the Milankovitch cycles, which, if you look at the cyclicity, which has to do with the position of the Earth as it rotates, whether it precesses, whether it has eccentricity or obliquity. It wobbles, it moves in relative to its position to the sun on a cyclical basis, not to mention solar irradiance, the sunspots, and how that changes over time. So we have this cyclicity going on, which is perhaps, there's no carbon dioxide variation here caused by humans. I don't think these guys that were around did enough driving of their cars and to emit the CO2. So let's now talk about this Holocene period. And so 12,000 years ago, we were coming out of the last glacial maximum, the LGM. And here we are, we're coming to this curve, really stable. This is where we are today in this period and through here. And depending, by looking at geological data from around the planet, northern hemisphere, southern hemisphere, different parts of different continents, we can tell what the temperature was with these different colored lines. And you can see that there are different parts of the globe that were as warm, if not warmer, than where we are today. And this whole period is called the Holocene climatic optimum. And I am running out of time. I just want to go through this because it's very important. Global average temperatures were probably warmer than now. While temperatures in the northern hemisphere were warmer than average during the summers, the tropics and parts of the southern hemisphere were colder than average. So there's this regional variation that's going on. The North Pole was warmer than 4 degrees C than it is now. The Western Arctic shows very similar warmer conditions than what we've got now. In northwestern Europe, they had periods of warming, as did northwestern North America, at different times. And that's what that curve, because it's gone, the multiple colored lines there shows. In Central Asia, current desert regions were extensively forested due to higher rainfall, and the warm temperate forest belts in China and Japan were extended northwards. Tropical reefs were warmer than they are now by 1 degree C at the Great Barrier Reef 5,000 years ago. Most interestingly, the Saharan desert was actually a green Sahara, in the African humid period, which took place between 12 and 6,000 years ago. And of course, humans settled it at that time. And in the southern hemisphere, we've got some observations as well. It was interesting because in 1977, this magazine came out, Time, with the big freeze, and there was a lot of worry and concern that But in fact, there's going to be a cooling, not a warming. And if we look at temperature versus solar activity, we've got two curves here, one shown in red, which is the temperature curve, and then the yellow curve is solar irradiance. It's just one aspect of the sun that we sort of see there's a relationship here. And until satellite information became available in the late 1970s, the consensus was that the sun was the cause of temperature fluctuations. But what we've come to realize is that from 1979, we've got this departure taking place. And so there's another question to be asked: what is the cause of that departure? And this departure is throughout all the data. And you can see relative to the baseline here that we've had in the last 20 to 40 years quite a substantial warming. It's a little bit out of character. And it all corresponds with the start of the collection of satellite data, which kind of is interesting. Because before that, we used land-based data, or we used radiosonde data, which is really the balloons that go up. But just looking at this period here from 1979 through to where we are today, there are all sorts of different satellites up there trying to measure temperature. They're not thermometers. They measure other things and then translate them into temperature. And of course, orbits change and these corrections have to be made. And so even amongst the satellite data, you've got quite a spread of what to believe. Similarly, an influence on the temperature is volcanic events. Mount Pinatubo went up in 1992 and emitted huge volumes, 42 million tons of carbon dioxide. Not a whole bunch when the humans emit 30 billion tons per year. But the main thing that Mount Pinatubo released were sulfate aerosols, and that brought a cooling to the Earth. Prior to that, we got these warming events, which correspond with El Nino events. This is a temperature phenomenon in the Pacific Ocean by and large. And when there's an El Nino event that's prominent, temperature goes up. But the Pinatubo took place in 1992, and with all the sulfate aerosols in the atmosphere, promoted cooling. And that's not the only time it happened. As you can see on this curve, I can't go back. There were, on that curve, a number of other volcanic events, each of which corresponded to cooling events. So we know that if we put things into the atmosphere, particularly sulfate aerosols, it will impede the UV penetration and the warming of the Earth. I think now is probably a good time to take a break. But I would like to talk about greenhouse gases, because they obviously are key to this whole business of reducing greenhouse gas emissions. So we have to understand what they are. And we'll start with this slide here, which lists 4 of the main contributors to greenhouse gases and the effect that they have in climate. On the left, you'll see water vapor and clouds. Then in red, you'll see carbon dioxide and methane. And then at the bottom, you'll see ozone. Now, all the climate scientists focus right in on carbon dioxide and name that as the big culprit. And maybe they're right in doing that. But the contribution from this chart that you can see to the greenhouse gas effect is between 9 and 26%. How does that compare with water vapor and clouds, which has an effect of 36 to 72%? And I don't want to diminish the role of carbon dioxide because it so clearly links to the fact that we have to burn hydrocarbons, and every time you burn hydrocarbons, that's what you get. And in fact, when oil and gas is formed in the subsurface, the methane that comes off in that maturation process migrates up to the surface, and it exchanges with the oceans, with the atmosphere, and converts to carbon dioxide. So methane has a role there to play too. But the presence of it in the atmosphere is, by and large, a lot less than carbon dioxide. 400 ppm plus or minus is the amount of carbon dioxide in the atmosphere today, or roughly. Whereas 1.8 ppm is the amount of methane in the atmosphere. That's 1800 ppb. In any event, what that really means when you do the numbers is that if I had a bathtub full of molecules of air, 2,500 of those molecules would be nitrogen and oxygen, non-greenhouse gas elements. And the reason for them being non-greenhouse gas elements is the molecular shape. They don't vibrate to the same degree that carbon dioxide does, and therefore they don't absorb or allow radiation to pass through it, according to this greenhouse gas effect. So they act very differently. So the culprit is carbon dioxide. And I make the point here that one molecule of carbon dioxide would be in that bathtub along with 2,500 molecules of nitrogen and oxygen. It's even worse for be one molecule of methane in amongst 500,000 molecules of air. So how is it that one molecule in 2,500 molecules can absorb radiation to the extent that it does? I find that absolutely mind-boggling. And of course, the pundits are saying, well, all you have to do is to take carbon dioxide out of there. This business of trying to sequester it and pump it underground and one thing or another. But first you have to extract it. And you can do that if it's being burnt in a chemical process somewhere. You can have a high concentration of it. But you cannot, in any way, shape, or form, come up with, and it's been tried, of filtering out of 2,500 molecules and get that one molecule of carbon dioxide, capture it, and take it and put it somewhere. It just doesn't, it's not feasible. I just thought I'd mention that too. But what's mainly important in this particular slide is the water vapor and clouds. Now, the IPCC, which is what I'm going to read to you in a moment, and chapter 7 in it addresses clouds and aerosols. And this is from the working group in the assessment report number 5, which is now about 5 years old. But it's the latest there is. And this is their attitude towards clouds and aerosols. These are the scientists talking, not the politicians. These are not the policy statements that have been taken by politicians from the scientists and then molded to what you want, what they think you should hear. So clouds and aerosols continue to contribute the largest uncertainty to estimates and interpretations of the Earth's changing energy budget. That's quite a statement. The quantification of cloud and convective effects in models and of aerosol cloud interactions continues to be a challenge. Climate models are incorporating more of the relevant processes than at the time of the previous assessment report, but confidence in the representation of these processes remains weak. Clouds are known to affect temperature and rainfall distribution, both spatially and temporally. And we can talk about cloud nucleation, ice crystals, and so forth. And I've already mentioned about aerosols. These have a similar major impact on radiative forcing, along with black carbon and sulfates. And I referenced volcanoes there. Let's go back to this let's ignore clouds and aerosols, because clearly nobody knows what their impact is and what to do about it anyway. And hopefully it doesn't really destroy or distort the models that are predicting all this future catastrophe. But let's look at the history of the concentration of greenhouse gases, what they call greenhouse gases, which is really CO2 and CH4, the methane and carbon dioxide, shown in blue and in green. And you'll notice that there are some curves there which represent NOxes and nitrogen compounds, which are also thought to be a greenhouse gas. And so you can see that the contribution to greenhouse gases is as shown here. Interestingly, When we breathe, we exhale 4% CO2. So now let's take some numbers and take our population. And what we find is that the emissions from our breathing is something like 1 billion tons a year, with a population of, well, in that case, 9.5 billion people. So that's a considerable amount. So what this statement says is that breath from global population contains 10% of the carbon dioxide emitted each year and growing as population increases. And in fact, in this room right now, we probably are at a very high level of CO2, depending on how they... Let's look at the growth in carbon dioxide and where it's come from. The blue obviously indicates that a big contribution from energy production and transport in orange and so forth, and we can see there's an increasing amount to the number somewhere around 35 billion tons every year. This is the annual contribution of carbon dioxide in the world. And here we are, the population. We've just, in 1 year, breathed 3.8 billion tons, so it's not a very big amount after all, but it's significant. And carbon dioxide emissions by region, well, you can see the growth here, and it's all taken place within the last 150 years, since 1850. And this is the distribution or the contribution to reach the 35 billion tons per year by region. And it really doesn't tell us very much, except that we're all contributing to some degree or another. In order for us to achieve reductions in emissions, we've got to look at where the carbon dioxide comes from. And this curve is insightful in that this amount of it is from coal, similar amount from oil, and a slightly lesser amount from gas. So if we need to reduce our emissions, we have to ask ourselves, how much can we stop burning coal? How much can we stop burning and to get those emissions under control? I'm going to skip through this because it's carbon dioxide. We often see pictures like this and we think, oh my God, that's carbon dioxide. Well, it isn't. Carbon dioxide is colorless. It's odorless. It's not a pollutant. It's essential to life. And that's about all we need to know. I can talk at length about, how there are exchanges between the atmosphere and the biosphere and the hydrosphere, the oceans, and there will be talks given through the series on that. But historically, let's look at carbon dioxide through that same period, the 542 billion year period, the Phanerozoic. Here we are again. We've got carbon dioxide up the side, and here I mentioned previously that I was going to show you biodiversity. Look at the growth in biodiversity in the Cenozoic period, which we spoke of a short while ago. And it's very interesting to see this huge proliferation in species and abundance, and it corresponds with lower amounts of carbon dioxide in Earth's history. And there are some issues around, therefore, to what extent does this biodiversity help sequester CO2 from the atmosphere? I've got to just spend a moment on this curve here because we've seen it before, but it represents the 400,000 years of the ice cores. And on the top we've got average temperature data from where we are today and the 4 peaks of the 10 glaciations that we're considering with the ice core. If we look at carbon dioxide, well, carbon dioxide peaks here slightly after the temperatures. This scale here is thousands of years. So first we have temperature rise, and then we've got carbon dioxide increasing. Which came first? Did carbon dioxide warm the planet, or was the planet warm? We had a lot of growth of plants and so forth, and the exchanges with the atmosphere producing this carbon dioxide. The other thing that's interesting in this is that the dust in the atmosphere, in the ice cores, every time you get these peaks of dust corresponds with this cooling period here. So it's a very insightful set of curves. Now I have to move to sequestration because this is a big topic in terms of how we manage going forward. There's this understanding that we have to deal with CO2, we have to fix it, we have to get it out of the atmosphere somehow. And we call this sequestration, CCS, carbon capture and sequestration. And here's a model of how it's proposed that we can do it. So we burn all our hydrocarbons that we bring up from the ground and produce the gas, which produces the electricity and the cement, and the petrochemicals are all here, and we capture from these processes the CO2, and let's say we put it in a big tank. Now what we've got to do with it. We've captured it, we've kept it from going up the stacks here. It's in this tank. So where do we take it from this point? And there are a number of suggestions that it can be dealt with through mineral carbonation, in other words, injecting it into minerals, building minerals out of carbon dioxide. Magnesite, MgCO3 comes to mind. I'll come to that very shortly. But the main way we're disposing of it is by putting it back underground, or we're putting it into the ocean environment. Where have I got the next screen up there? Well, this has been tried and is very successfully applied in where? Saskatchewan, in Weyburn and Mydale. And here are some oil fields, 2 oil fields, Weyburn and Mydale, which are now being used to store CO2. The CO2 comes from Beulah in North Dakota in the States, and it's piped. I think it's 300 kilometers or so north across the border, and Canada takes it and takes the CO2, and the CO2 comes from a coal gasification plant in Dakota, and it produces 8,500 tons of this CO2 a day. And it's accepted by the producers of oil from the Weyburn and Mydale fields. And in fact, it's called EOR, Enhanced Oil Recovery. The EOR system then takes this carbon dioxide and pushes it underground, pressurizes it through the formation, and pushes out the oil. Some CO2 comes back to the surface, it's stripped out, and then it's recycled backwards again. Ultimately, there will be a CO2 buildup underground, and that is what we mean by sequestering. But the interesting thing is that there's no big hole in the ground that this stuff is going into. All holes underground are filled with 3 things. One is water, one is oil and gas, and not much air. But so really, it's oil, gas, and water. And if you're going to put something down there like carbon dioxide, it has to displace that stuff. And I don't think we understand what that requires in terms of the amount of energy, the amount of effort and the cost, and whether it will be contained underground. It's a whole bunch of questions. So this whole business of sequestration geology is very frightening to me, and we just conceive of it in the various people that are projecting out into the future, and they say that in order to capture this CO2 and sequester it, we need to take 690 depleted gas fields. We need to take 120 depleted oil fields, just like the Weyburn one that I just talked about. And we need to put it into these saline aquifers. Well, what does that mean? It means displacing water underground and pushing the CO2 in there and hoping it stays. Or we could put it in unminable coal seams. Wasn't that a thought? So I think this whole idea of sequestration geology needs a lot more work, and I'm not convinced in my own mind that it's the right thing to do. This certainly isn't the right thing to do, putting into the ocean, and yet it's being considered. And so what they're thinking of doing is liquefying it and putting it down into the deepest parts of the ocean, which would be about 4,000 meters deep. and hope that it stays there. Or you can do an intermediate injection and wonder where it goes and what's going to happen to the chemistry of the ocean. So what are the risks and what's the capacity? One good way to sequester carbon is to produce plastics. And I think that's an ideal thing to do. It locks it into the plastic. We can't get rid of plastics. They seem to survive for a long time. We should just make a big pile of plastic, and that will sequester the carbon. Now, I did mention that there's a project underway to inject CO2 into the rocks, and with appropriate temperatures and pressures, we can form this mineral called magnesite. And it's a project that's underway in the Oman. And in fact, it's being considered here by Ocean Networks Canada, looking at some of the rocks that are just offshore here. And the idea would be that they would liquefy carbon dioxide and drill into the ocean floor basalts, which have a large amount of olivine minerals, or magnesium-rich minerals. And by putting CO2 into it, we convert that magnesium mineral from being a silicate into a carbonate called magnesite. Well, that's an interesting thought, but can you imagine the cost of doing that and how you capture your carbon and liquefy it and move it out there, drill those wells offshore? It's difficult to do it. So there are two imperatives. The planet is running out of oil, burning hydrocarbons at the rate causing runaway global warming. What can we do? Substitution, reduction in consumption, sequestration, and we end up with this net zero emissions. And we're going to have a breakdown, but we're not. We've already had it. So I have to move on. That's how far behind I am. ROEI, I've got some notes somewhere, but I think I can do it without the notes. It might be shorter. What we see here is that list of energy producing from energy producing sources. And here I've separated out the early oil, the cheap oil, the easily found stuff, the big stuff, from the more conventional oil, and then what we face right now, oil that I call an average oil and has a large component of shale oil. And what we're talking about here is a ratio of the energy delivered on the top divided by the energy required to deliver that energy. So it's a ROEI, it's the energy return on energy invested. And it gives us a number which I think is very meaningful. Obviously, the bigger the number, the more energy we're getting out of whatever it is we're producing from. When we get down to 1, it's break even and we're wasting our time. But as you can see, the green ones, which are the non-hydrocarbon source supplies of energy, there are 2 or 3 of them which look like they're worthwhile considering. Wind, CSP, solar. What do we mean by CSP, solar? Distinguished from photovoltaic cells. This is where you have a series of mirrors which focus into a central pillar, and the energy from the mirrors reflected onto the central melts salt, and then from salt you can then generate electricity. This is going to be a subject which we'll go into. But that seems reasonable. Hydro is quite reasonable. Nuclear certainly is reasonable. Anything over 5 is considered worthwhile. But over time, you can see that ROEIs change. Oil, for example, has come down from that large number down to a lower number because it's now more expensive to produce oil than it used to be. And it also changes in the case of solar here, where the early technologies were fairly inefficient and they've improved in efficiency and technology, and so the ROEIs have gone up. And we have to, in making these comparative statements about which ROEI we should think is good or bad, we have to take all the numbers into consideration. So when we're looking at nuclear, we have to consider, well, We've got a huge capital infrastructure, same with hydro dams. We've got to amortize that over a period of time. So we can't just take how much does it cost to build a solar cell? How much energy does that solar cell produce? It's a very complicated, it gives the economists something to do. And it has to take everything into consideration, the mining aspect, the transportation, and so forth. Well, now here we are. We're moving forward now into the first of our series. This is on February the 8th, not this Saturday, next Saturday. And Nicholas Pocard from Ballard Power is coming, and I don't think he's going to ride his bike. But this is interesting. I saw this picture and I thought, oh, that's wonderful. You heard electric bikes. Well, here's a hydrogen fuel cell bike, and you're sitting on a canister of hydrogen, and it's rather the imagination rolls. But hydrogen has its challenges, but more to the point, the production of hydrogen is problematic, and I mentioned this before, because there are two ways to produce hydrogen. One is through electrolysis of using electricity and a membrane. That's one way. So you need lots of electricity, and you need the material that you make your membrane out of, which costs money and not always easy to find. The other way to produce hydrogen is steam reform methane, and of course in doing that you release a lot of CO2. So it becomes a bit of a difficult proposition. I was going to mention something about geothermal, and I might just be able to squeeze this in. Geothermal power is of really two types. One is actual power generation, for which we need steam to turn the turbine, and you need steam. Of course, that means 100 degrees C boiling water, unless you want to compensate for pressure. But there's also a binary style, which will be a closed-loop fluid, in this case isobutane, which boils at a much lower temperature. So if you can't get the high temperatures because your thermal gradient isn't there, you can get a lesser temperature, and using a closed-loop system, you can boil your isobutane and turn a turbine and produce electricity. Well, unfortunately, geothermal electrical power is expensive, it's unpredictable, it's unreliable, very site-specific, and its ROI is not the best. Now let's distinguish that from a ground source, and you've probably thought a lot about ground source. I know you have. You're wondering how to heat your home, and you've heard of people, drilling into the ground and heat exchanging with warmer air that's in the ground. It doesn't have to be boiling, of course. And there are some major projects that do this, and they can take advantage of what we call a normal geothermal gradient of 25 degrees C per kilometer. So for every kilometer you drill down, temperature goes up 25 degrees C. Not saying that you would, for a ground source, need to go to a kilometer, but you'd get warmer as you go down. Installed geothermal capacity, very quickly, it's very limited. It comes out to 14,000 megawatts or 14 gigawatts. And these are the main countries in the world that produce it, and there's the percentage contribution to each of their national electrical requirements. So as you can see, it's not a great contributor. But the IPCC feel that there's a capacity expectation of 35 gigawatts to 2,000 gigawatts. They have no idea. Here, this is 14.3 gigawatts. The current installed capacity is a fraction of what the IPCC think is out there. And currently, they think that we've only tapped 6.9% of global potential for geothermal, and I find this very difficult to believe. I just want to look at one specific thing. This is Hawaii, and everybody has been to Hawaii, maybe even to the Big Island, which is what's shown here. The Big Island is sitting on top of what we call a mantle plume or a hotspot, and the geothermal gradient is very high here. Here's the Big Island of Hawaii, and the other ones are sinking, as this sort of indicates here, because after an island is formed, the plate moves off in this direction, it cools, and as it cools, it subsides, and it actually forms a whole bunch of these features. Now, why am I saying this? Well, because there is a geothermal plant owned by Puna, and it's very near to Hilo on Hawaii. It's also very near to where the eruption is, Kilauea, and this is the mantle plume, high geothermal gradient, very high. In fact, comes right to the surface here. And of course, it opened in 1993. It's a 38 megawatt plant. You can see it in the photograph there. But unfortunately, a couple of years ago, it got taken out with the. It was too close to the geothermal gradient, to the volcanic event that took place. They have 11 wells. They're planning on drilling a couple more once things settle down. They go down 3,000 meters, and they hope to build capacity up to 46 megawatts. This is the demand for electrical power on Hawaii, and you can see in this orange color what the contribution is from this Puna plant historically. Of course, it's not producing now, but it's going to come on very shortly again. Ground source heat. Remember, I was talking to you about that. This is a great example of a project which is just coming now, second quarter of this year. They've drilled 2 wells, 6,400 meters deep, 6.4 kilometers deep, in order to achieve some hot water, but it's not enough to drive a turbine and produce electricity. So what they're doing is district heating a whole bunch of buildings in Finland. I don't know how economic that is. I can't believe for a moment that it's economic. Biofuels. I just want to mention biofuels very quickly. There are 2 types. There's ethanol and biodiesel. We can make liquids from anything. We can make it from coal, gas, grain, in this case, corn, ethanol, sugar, soybeans produces the biodiesel, animal wastes. And I mentioned earlier, a long time ago in the talk, that the Fischer-Tropsch German process was developed in 1926 to take coal and produce liquids. So let's talk about ethanol. ROI is very low, basically around 1. Here's some numbers. 1 acre of corn produces 328 gallons of ethanol. And now you've got to worry about how you fuel your tractor, how you make your fertilizer, how you distill the fuel once you've got it. And at the end of the day, ethanol is 34% less energy per unit than a volume of gasoline. And therefore, you're not going to get the same mileage. In fact, you have much reduced mileage, 34% less mileage. And in order to fuel all the cars, we'd need to grow corn in the entire U.S. It's rather ludicrous, and of course, it's all to promote farmers and jobs and so on. And at the end of the day, because we're making alcohol or ethanol, we have to add gasoline to it in what they call a denaturant, so that people won't go around drinking it. And that's 15%. That's why you see ethanol 85. Now, biodiesel is made from soy and canola. And of course, we could make it from a whole bunch of other things too, animal fats, palm tree oil, and so on. I'm not going to go into this, but it's controversial because of land clearing that's required, subsidies to farmers. That's a huge thing. And at the end of the day, we're still burning hydrocarbons. And we're still releasing CO2. So I don't see biofuels as being the big savior towards reducing emissions. They talk about sequestering by growing crops. And that's fine as long as you don't cut them down and burn them and try and make fuel out of them. So let's leave the crops to grow, let's plant the trees, and let's sequester carbon and carbon dioxide in that way. I don't think we're any further ahead by considering biofuels. And if we just look at the history of biofuels, it's relatively recent. In the last 10 years, we've seen quite a bit of growth in it. It's being encouraged politically. You can see in North America the lime green at the base there, how significant it is. And in fact, the growth from this curve on this feature here on the left side was what it was in 2018. And what we're looking at here is ethanol in this green color here. And then 2008. And then 2018 in North America, it's grown that much. Whereas in Europe, what we seem to find is that they use biodiesel, and it's got more substantial growth. Regardless, I'm not sure that biofuels is the way to heaven. Now, I do want to say a few words about the economic impact. When people talk about let's not burn oil. We don't need oil. Let's live without it. Well, by saying that, you have to understand that there's going to be a financial impact in Canada, in particular Alberta. And this book, From Miracle to Mess, by David Yeager, who's a columnist in Calgary, so he's quite biased in his point of view. He's very pro-industry. Decarbonizing the industry and the energy complex will require the largest financial disruption in history, affecting everyone and everything. And he points to these statistics that in the last 8 years, the net transfers from Alberta, $180 billion, the most of all provinces, 4 times as much as what Ontario has produced, even with the Alberta population being a lot less than in Ontario. BC's a contributor in the net transfer, and then you can see the recipients in red there. So we do away with the carbon resource industries, and that's what we're going to sacrifice. Of course, we won't do away with it entirely. We'll just reduce the amount that we what we deem we should need. The GDP contribution, oil and gas in Alberta, in Canada, as a matter of fact, in 2017 from Stats Canada is $101 billion. Well, the next biggest industry is mining, at a fifth of that, and the famous vehicle constructions and parts and so on in Ontario and other places is a fraction of that, and so forth. And direct jobs, well, there are 650,000 of them according to Syria, and they pay taxes of $40 billion. So finally, this third slide that sort of speaks to the wealth in Alberta that the oil industry has provided, is that the chemical industry that's linked to the oil and gas production, Alberta produces 47% of Canada's chemicals. All those jobs, and the value of the exports is staggering. I won't go through what a barrel of oil yields, but at the bottom of it you can see that there's a whole bunch of petrochemical feedstock. And of course we've talked before about what the products are, the fabrics, the ammonia, the sulfur, the polyethylene, and the plastics. Now, moving quickly to the conclusion, there are a number of organizations which put out data that look historically at what consumption patterns have been, and they also forecast what they might be. And of course the IPCC is one of those, and we speak of the Paris Climate Accord of 2015. Well, there's been 33 of these conferences over time. 6 major agreements, Kyoto, Copenhagen, and now Paris, 3 of them. There are other bodies such as the US Energy Information Administration and the International Energy Agency. The same letters, just reorganized a little differently. That's an OECD organization. I'm going to skip Irina and I'll go to BP because that's what we're going to talk about next. And I'll finish off by talking about Shell. Now this gentleman here, Spencer Dale, he's BP's chief economist. And every year they put out a World Energy Review. It's a statistical review of consumption of different components of energy. And it's the go-to resource. All bodies go here. BP are particularly adept at doing this. He made a couple of statements which are at the end of the last one, 2019. At a time when society is increasing its demand for an accelerated transition to a low-carbon energy system, the The energy data for 2018, which is the data that's gone into the 2019 report, paint a worrying picture with both energy demand and carbon emissions growing at the faster rate seen for years. So he goes on to say, what does seem fairly clear is that the underlying picture is one in which the actual pace of progress is falling well short of the accelerated transition envisaged by the Paris climate goals. It's quite a statement to make, and it's very precautionary. Let's look at some of the data. We see world consumption of energy increasing. The different commodities, coal in black, oil in green, gas in red, and then there's the nuclear energy and hydro and renewables. And that's the makeup of it historically over the last 25 years. We see oil on the left, the history of production of oil by region is shown, and you can see the Middle East is a big producer in orange. But the growth on the right, the consumption, different from the production, the consumption shows a lot of growth in the Asian markets. Natural gas, well, just continues to go up. Coal is a different subject altogether. Basically, outside of Asia Pacific, and here we have to include Australia with Asia, you can see that on the production side, Australia is a big producer, and that accounts for this huge increase in the amount of coal produced over the last 25 years. On the consumption side, you can see that that would be made up of China, India, and Korea. But interestingly enough, the growth is finished, or it's flattening off of about 8-10 years ago. So there's some hope going on there. Nuclear, little or no growth. Hydro, little or no growth, except in China. China are really optimizing their hydro. Renewables, well, rapid growth in renewables in all regions. But when we look at the subsections of renewables on the right, we see solar in yellow and wind in blue and other in gray. But you can see the biggest growth is in wind. Now, the good news is that the annual additions to the generating capacity, electrical generating capacity, is that it's continuing to grow. So non-renewables, such as the hydrocarbon sources of electrical generation, are declining. And renewables account for 60% of new electrical generating capacity. I won't go into this to any degree, but Europe leads the way on renewables, shown by the green line and my little flag there. So BP data shows the last 20 years of growth in production and consumption is significant. Can we expect to slow or stop this growth? Can we change how we produce the energy? Can we offset the products of combustion by sequestering carbon? And now I'm going to talk about Sky. Sky is Shell's proposal, a pathway for the rest of the century. And they've independently come up with this, and you can see the website there, it's publicly available, but they've looked at the century remaining ahead of us. And they say that they feel it's achievable to reach the Paris goals, to meet the Paris Agreement. And we know what that means. In this case here, it's net zero emissions by 2060, 2070. They make the statement that the pathway requires strong government leadership. You bet it does, but not necessarily forthcoming. They think that we can get well below the Paris targets through emissions from different sources being reduced, and from sinks, the sinks of the greenhouse gases, in other words, sequestering and putting CO2 away, and with the objective of net zero emissions by 2070. Shell wasn't just new to this game. I remember back in 1997 they established a renewables division. They put $100 million into it, and they started to think about, should this be an area of energy production that we should get into? And they did. They went and produced something called Shell Solar and Shell Wind Energy and funded a whole bunch of projects. I just mentioned that as a sideline. But now they've come back to produce this document quite recently, just in the last few months, and it's called Sky. Because we need energy for just about everything we make and do, achieving sky essentially involves rewiring the whole global economy to reach net zero emissions in just 50 years. The challenges: population growth, an increase in energy demand growth. I think you saw that earlier on. Stark reality of the earliest 21st century is the role that coal plays. And it's hard to get away from the fact that we do need coal in terms of producing chemicals and smelting and so forth. So the other challenges that we've got to worry about the lack of low carbon substitutes. We don't have them for aviation and shipping and road freight and cement manufacturing. So these are the challenges. Wind and solar power can grow rapidly, but produce electricity which makes up less than 20% of final energy consumption today. It's got to triple. It's got to triple. Huge growth. And some promising low carbon technologies such as hydrogen and carbon capture and storage, they admit we've got to work on those quickly. They're nowhere. So they make the statement that they've got to embrace the whole, societies as a whole have to embrace this whole initiative of making these changes. The vision then is to achieve net zero emissions by 2070, and it's increased electrification. Well, isn't that news? The increased replacement of direct fossil fuel, such as gasoline for mobility, by electricity, and perhaps by hydrogen for air travel. How else are we going to fly around the world? Electricity exceeds 50% of end use of energy consumption, 5 times the size of that seen in 2017. That's what they're anticipating. That's their vision. Fossil fuels are effectively absent from power generation, with solar starting to dominate. And electrification means that we're going to have to phase out the combustion engine, and that by 2030, half of the global car sales will be electric. By 2050, they'll all be electric. And we've got to electrify rail corridors, as they do in China and Europe and Japan. We've got to do it in North America in infrastructure development. And this is where I have real trouble with them. Biomass generation has emerged, linked with carbon capture, to offer an important carbon sink. I think this is a huge challenge. And finally, they end up with this notion that we should get governments to put in place carbon pricing. I've just got a couple of minutes to conclude here. This carbon pricing comes in the form of taxes, levies, and market mechanisms. And what they're suggesting is that by 2030, all the governments will agree on what those should be. And I'm going to quickly go to a slide which shows that. This simply shows the degree to which electricity is going to displace other fuel sources, other energy sources as we go forward to the end of the century. I think we've gone over a lot of this already, but for example, they're talking about the need for 10,000 carbon sequestration plants compared with 50 that are in existence today. Net zero deforestation, but we've got to reforest areas the size of Brazil. This is a form of sequestering carbon dioxide into plants and trees, as long as we don't cut them down for fuel. And nuclear, down at the bottom there, I think they've missed the boat on that one. Why is it going from 5 to 11%? And they create this little cartoon here showing the current day emissions of 35 gigatons of carbon dioxide, but they have bioproduction of carbon dioxide to the tune of 6.7. And they say that's got to change. So how does it change? Well, we'll halve the amount that we're taking for fossil fuels, and we'll increase the amount from biofuels. And we'll then put a whole bunch of stuff into the ground sequestering carbon dioxide. Doesn't make a lot of sense to me. Now this is coming back to the carbon pricing thing. I've just got 5 minutes. This is their graph showing that carbon pricing needs to get in place now, and that the dollars per ton of tax that would be applied to carbon dioxide will go up according to the red lines here. Well, hello, Canada is already proposing, Trudeau, that by 2022 we'll have $50 a ton. And then he's already proposing that by 2030 we'll have $210 a ton, and that adds 40 cents to your gasoline bill. So it's interesting that we consider that the government can do this and should do it, and that by 2030 it'll all be agreed to and it'll be on its way. What it does is speeds up the construction of gathering carbon dioxide into central facilities and then worrying about how to dispose of it. The next thing, the second point, I just don't understand what it means. Drives the deployment of net negative technologies like bioenergy with CCS. It doesn't make a lot of sense. But what is apparent is that certainly in Sweden, by putting in place carbon taxes, carbon levies, as we're talking about, it does decrease the consumption and therefore the emissions of CO2. It's been proven over the Swedes were the first perhaps to do it. They've been doing it for 15 years. And they have a horrendous tax. And apparently it's dissuading people from buying fuel, and as a result emissions have dropped. But what do the governments really do with the revenues? They're talking about returning it to consumers, and I just don't understand that. I don't understand why they would take it away on the one hand and give it back to you in another. Wouldn't it be better if they created a pool of dollars for technology development? And I'm sure you've all got your own ideas on what the government could do with a big bucket load of funds from taxes. Hydrogen, we'll learn more about that, and Nicholas's talk coming up. But it doesn't really enter into the situation until 2040, so we've got 20 years to figure it out. And battery costs, this is for Dr. Rowe's talk. Shell anticipate that the cost of batteries are going to go down as we get more clever at it. So in a nutshell, it's just huge growth in solar electricity. And this growth is both from wind, shown in pink, and solar. In 50 years' time, that's what it's going to look like. And in order to do that, we have to do some tremendous things in electricity generation. And I'm not going to go through them, but they are staggering, absolutely staggering, and quite daunting. So can we live without oil? My opinion is no, and if we look at this curve here, this set of graphs, by 2070, which is the deadline, we're going to be down to 20%, but that's fossil fuels. Sky contemplates a whole bunch of biofuels contributing to the mix, and I'm not sure that that's the right direction to go. But according to Shell, and it's worth a read, it's worth going to that website, and I will post this whole presentation on our website, so you can access their website. And it's worth a read and consider it, because I have not seen anything close to this that has been put out by any other organization. And it's not just because I'm a retired Shell employee. So, closing statements. In my opinion, we will never run out of hydrocarbons. The commodities will become increasingly more costly to produce, whether from fossil fuels or biofuels. Hydrocarbons from either source release greenhouse gas emissions upon combustion. Combustion of hydrocarbons is essential to human existence. There are no substitutes for petrochemical products or ways to produce fertilizer, steel, and cement without hydrocarbons. We cannot construct roads and highways. There is no alternative way to power aircraft. We cannot live without oil. Imperative number 2, because you remember that was imperative number 1, we're running out of oil. Imperative number 2, the Paris ambition set by IPCC is to achieve net zero emissions of greenhouse gases by 2070. It doesn't say how. What I've just tried to present to you is Shell has this pathway called Sky, and it claims that it can meet those Paris ambitions. I have a lot of concern about Sky. I think there is much wrong with it, but it's worthy of discussion and debate. It's a template. If we accept the climate modeling as settled science, and we believe in the premise that ground GHG emissions are causing global warming to the extent that we think they are, can we look at past actions taken by mankind that have had an impact on the atmosphere and climate? And I leave you with two things. One is the Montreal Protocol that was successful in 1987, when in 1973, two gentlemen who won the Nobel Peace Prize saw the damage being done to the ozone layer by halogens. That's one. And the second one is Haber-Bosch, the German invention in 1919, which led to two more Nobel Peace Prizes, where they saved the world by creating a way of producing fertilizer, which enabled the crops and the fields to feed the world as the population has grown to the extent that I've shown it. Both of them deal with the atmosphere, and I think I'll leave you with the thought that we're intelligent human beings here, and that going forward, that I feel optimistic we can deal with these situations and come up with solutions. It's just that I'm not sure what they are right now. Hope this series that you're about to embark on will help you better your understanding. And I hope you'll attend it. We were supposed to have 200 people here tonight. That's how many registered, but it is free. So a lot of the people that maybe looked at the weather and said no. However, the series starts on the 8th of February, and I would like to see you all come to those talks and hope we can have a good exchange of ideas throughout the next 2 months. So thanks very much for coming tonight and for your attention. Appreciate it.